Let us continue this brief introduction into relativistic cosmology. An important notion is the so-called cosmological principle. It states that universe is same at a given time, it's same in all directions and at all locations. This is what's described as homogeneity and isotropy. In a sense, cosmological principle is the generalization of Copernican principle, but on a global universal scale. Now, there is a perfect cosmological principle proposed by Hoyle and collaborators, which says that the universe should be also the same at all times. And that was the basis of the steady-state cosmology, which unfortunately did not survive experimental tests. So what do we mean by isotropy and homogeneity? The picture on the left is homogeneous. You can be anywhere in an infinite plane covered with its stripes and it look the same. But it's not isotropic. The stripes have a given direction. So it's not the same along the stripes or orthogonal to them. The picture on the right is isotropic from the point in the middle. Same in all radial direction, but it's clearly not homogeneous. And here we have an example. It would be homogeneous and isotropic texture that is same everywhere in all directions and all places. And the one on the right, which is neither homogeneous nor isotropic. Why is this important? Well, is it really true? Well, it is true on scales larger than about 100 megaparsecs. And there are a couple experimental pieces of evidence for that. The map on the right shows positions of radio sources in the sky. Those tend to be very far away. And so they're a fair sampler of a universe's volume. As you can see, it does look pretty homogeneous. The ellipse on the lower left is indicative of what cosmic microwave background sky looks like. Very uniform. There are fluctuations in it, but they're parts in a million. So that tells us that indeed the universe at very large scales is homogeneous and isotropic. Not so on scales smaller than about 100 megaparsecs, where we see all the large-scale structure, filaments and voids and so on. Turns out that doesn't really matter so much as far as cosmological tests are concerned, and cosmology really operates on scales of gigaparsecs and larger. So it's true that locally, the universe is not homogeneous isotropic. You are standing on a planet after all, but on large enough scales, it is a good approximation. Let's go back to general relativity. Remember, the most important notion is that presence of mass and energy determines geometry, and geometry determines where mass and energy go. And the two have to be consistent. So getting a consistent solution to that is essentially Einstein's equations. We will not derive them here in any shape or form. We just need to show you a little bit of what they look like. So we start first with Poisson equation, which describes gravitational potential phi as a function of density rho, and this is true in Newtonian physics as well. Now, general relativity says that gravitational potential can be also made equivalent to geometrical description through the metric tensor. And there is, instead of plane density, there is so-called matter energy density tensor. And that is a matrix 4 by 4, and we need not go into its details. It's a shorthand notation, so using the two indices, mu and nu, which go from 0 to 3, this represents 16 partial differential equations of this form. And those are the Einstein equations. So basically, thing to remember. On the one side, there is a term that is all about space-time geometry. And on the other side, there's a term which is all about mass and energy and where they move. So this is what Einstein's equations are really all about. So there's 16 of them. But we made those important assumptions that the universe is homogeneous and isotropic. And that means that only one coordinate would matter, radial coordinate. So that makes things much simpler. Instead of 16 equations, we only have one. And that is what's called the Friedmann equation, which is the basic staple of cosmology. Just one more thing. Gravity, as you know, is an attractive force. And this is certainly true in the universe at large as well. But Einstein's equations allow for introduction of an additional term in potential. And you can think of it as, say, integration constant, or a new phase of gravity, just like electricity and magnetism are two phases of electromagnetic interaction, but something that's only apparent at cosmological scales. Essentially, this corresponds to constant energy density term. And that is what's called a cosmological constant. Now, if it is seen as, say, integration constant, we have no idea what it is. The theory doesn't give us its value, and we don't even know its sign. It can be attractive force or repulsive force. Turns out it is a repulsive force, and it is actually very important, but we'll cover that later in the class. So those are the basic notions of relativistic cosmology. Next time, we'll talk more about the expanding universe and what that means.